Hi, welcome back to our 11.7 notes. Where we left off last time, we had just finished graphing, and we had an interesting graph that didn't have any x-intercepts at all, versus the first graph that we had that had two really nice, pretty x-intercepts that were easy to find. So one thing that you guys might be wondering is, how do I know if there are going to be x-intercepts or not, and can I find that easily? And the easiest way that you can do that is actually to look at the discriminant. So if you guys remember, the discriminant is b squared minus 4ac. It's the thing underneath the square root in the quadratic formula. And so if you can find that discriminant, you can figure out how many x-intercepts you have, if they're going to be rational or irrational, based on that discriminant. So just a quick refresher with the discriminant. If that discriminant ends up being positive and being a perfect square, then you're going to have two rational answers, which means in this case we'll have two rational x-intercepts. Okay? If it is positive, but it is not a perfect square, what that means is that you'll have irrational x-intercepts. It's still going to cross the x-axis, but not at a nice pretty point. Okay, so we're talking about causative, not perfect square. You're going to have two irrational x-intercepts. And if you want, you could put that, you could find those irrational x-intercepts, get a decimal approximation, and plot that if you want to. My math lab, of course, won't let you, because it likes nice, pretty integer points. But that is a possibility if you're graphing something by hand, or you just want to know where does it cross the x-axis. Okay. If that discriminant equals 0, that's a pretty special case. That means that your vertex is on the x-axis. So you're actually going to only have one x-intercept, and it's going to be the vertex of your parabola. So you're going to have one x-intercept, and it'll be the vertex. Okay? So it's going to sit on the x-axis. Okay? The last option is if you have a negative discriminant, that means it will not cross the x-axis. It doesn't have any real x-intercepts, only imaginary one, and we don't graph imaginary stuff on the real coordinate graph, so no x-intercepts. Okay, so that's how you can find things quickly and easily. Okay. The next thing we're going to look at is some application problems that use the vertex. And so the vertex, so either you have a parabola that is going up, or you have a parabola that is upside down, right? So if you have an upward shaped parabola like a U, the vertex is at the very, very bottom, okay? So what that vertex will represent is a minimum of something, okay? So the x-coordinate will tell you where that minimum occurs, and the y-axis tells you what the minimum is, okay? If it's a downward shaping parabola, which means that your a value is negative, the vertex is at the very, very top. And so that vertex would represent the maximum of something, okay? And again, the x-coordinate of that vertex would tell you when it happens, or where it happens, and the y-coordinate would tell you what the maximum value of the function is, okay? And that's really what you're doing with all of these, is finding minimums and maximums. Let's do some. First thing we do is, we have in part A, a farmer has 100 feet of fencing. He wants to put a fence around a rectangular field next to a building. Find the maximum area he can enclose and the dimensions of the field when the area is maximized. So let's draw ourselves a picture here. Okay? So we have a rectangular field that's next to a building. Okay? So we have a building. I'm not very good at drawing, so I'm just going to draw a box with a B in it, okay? And so he's going to enclose a fence next to that building. And I don't think it touches, it doesn't say that it touches the building. Alright, I'm thinking that they gave us the building as a hint, okay? So let's assume that the building is one of our sides. So I'm going to draw that again. So here's my building, and what's happening is that you're going to have this rectangle next to the building, so we're going to assume that it's touching the building. And so the building will be one side, we won't need fence where the building is. Okay, so our rectangle is going to have 2 lengths and 1 width. Okay? Looking at the rest of our information here, the farmer has 100 feet of fencing. So what that 100 feet is going to be is the perimeter of the fence. So that 100 is going to equal these 3 sides added together. So all of our fencing added together. So that would be 2L plus W would equal 100. Okay? Then, let's see, down here it says find the maximum area. So we're trying to find the maximum area, which means I need to set up an area equation. I know that I'm trying to find a maximum, which means I'm trying to find the vertex of a downward parabola. Okay? So let's go ahead and set up an area equation. So area of a rectangle would be length times width. And let's go ahead and substitute for one of the variables so I don't have 2 variables in there. So from here, I think the easiest one to solve for is W. So if I subtract 2L from both sides, I would have W equals 100 minus 2L. And then I can substitute that into my area equation. So then area equals length times 100 minus 2L. Okay? So just distributing that out, I would have area equals 100L minus 2L squared. Or if you like that in standard form, because it's kind of nice to have the L squared first, that would be negative 2L squared plus 100L. So that would be my area equation. Instead of having X's and Y's, I have A's and L's. Okay? But it works the same way. So now I have a nice area equation. I can find the maximum. Remember, the maximum happens at the vertex. It is a downward shaped parabola. I know that because my leading coefficient is a -2, and the negative will flip it around so it's going down. Okay. So finding the vertex so that we can find the maximum. Instead of x equals, well, this time I'll have L equals. So L equals the opposite of B over 2A. So for us, my B value is 100. In case you're curious, my C is 0. But my B value is 100, so the opposite of 100 would be -100. And 2 times A, 2 times -2 would be -4. So -100 divided by -4 would be +25. So my maximum area happens when my length is 25 feet. Okay? Let's see, find the maximum area he can enclose and the dimensions. Well, the dimensions are probably the easiest thing to find next, okay? So if my length is 25 feet, my width would be 100 minus 2L, so 2 times 25 is 50. 100 minus 50, so my maximum width would be 50 feet. So here's my dimensions, are 25 feet by 50 feet. And then for area, you've got your choice. You can either do length times width, which is probably the fastest way to go, or you can plug the 25 back into the area formula, and you should get the same answer either way. But I would say your maximum area, let's just do length times width. Let's do 25 times 50. And 25 times 50 is 1,250 square feet. So there's your max area. So that found everything. So that's kind of what these look like, is that you're going to have some sort of an equation at some point, and then you're finding the vertex to find the maximum or the minimum. And in case you're wondering, what's the keyword that I'm trying to find a vertex? Maximum or minimum, okay? Let's do another one. The next one says, a toy rocket is launched from the ground so that its distance in feet above the ground after t seconds is right here. All right, so we've got s of t equals negative 16t squared plus 208t. Find the maximum height it reaches and the number of seconds it takes to reach that height. So I'm going to give you guys a second. All I want you to do, here's your equation. It's already made for you. Find the vertex. Okay? And then we'll talk about what those things mean. Okay? So, pause your video, find your vertex, and I'll show you the answer in 3, 2, 1. Alright, the vertex you should get, the t-coordinate is 6.5 or 6.5, and the s of t coordinate is 676. Okay? So what do those things mean? That's your t, that's the time that it takes to reach that maximum height. And the 676, that's your s of t, that actually is your maximum height. Alright, so when it says find the maximum height, your max height is 676, and let's look at units. We are in feet. For the number of seconds that it takes to get there, that's this answer, which is 6.5 seconds. And that's it. Not so bad, right? Good. Alright, last one. Between 1989 and 1998, the population of small-town USA in thousands can be modeled using this equation. So we've got the equation right here. So where x is 0 represents the year 1989. Based on this model, in what year did the population of small town reach its minimum? So this one has a positive x squared coefficient, so it's an upward shaped U like that, and we had a minimum at some point. Again, you're finding the vertex. So I'm going to give you guys a minute. Pause your video. See if you can find the vertex. So pause your video, and I'll show you the answer in 3, 2, 1. Alright, the vertex that you should get for your x-coordinate, you should get 7. For your y-coordinate, you're going to get 8.02. So let's talk about what those things mean really quick. So the 7 is actually your years since 1989. So that's years since 1989 that minimum happened. And the minimum population is right here. That's your minimum population. And in case you're curious, that was apparently in thousands. So your minimum population is 8,020 people. So that's the lowest that they got. But this only asked for in what year did the population reach its minimum. So you're actually not interested in that 8.02 at all. We're only interested in the 7. So in 1987, x was 0. This is 7 more than that. So what I'm going to do is take 1987, add 7 to it to figure out what year the minimum happened at. And 1987 plus 7 is 1996. So that's the year that they had their lowest population. Okay. Hope this helps. We'll continue on with our last section in our last video.